I was solving this problem, right? Problem number 7. So today I have to go a little bit fast because you have lots of syllabus. It is another problem, problem number 8. So in this problem, it is seen that a solid shaft. This is a solid shaft, and this solid shaft is inserted or buried to the soil using a torque wrench. This is a wrench. This is known as torque wrench because torsional force can be applied through this wrench. That's why it is known as torque wrench. And the inserted or buried length is 24 inches, and above the ground to the end of the torque wrench, its length is 36 inches, and the diameter of the shaft is 2 inches, and the applied torque is produced by applying 2 equal force, and the magnitude of force is 25 pound, and the lever arm between the forces is 6 plus 6, 12 inches. Okay, and here due to frictional force, torsion will be developed. Okay, that will be the internal torque, and the properties of the material of the tube or the shaft. Properties means the modulus of rigidity of material of the shaft is 5.5 into 10 to the power 3 KSI. So now we have to determine the maximum stress in the post, or you can say the post means this tube. So we have to determine the maximum stress in the post and also the angle of twist of the wrench. So what is the angle of twist of the wrench with respect to the other end of the post? Okay, so to determine the maximum stress, we have to determine the maximum torque. Okay, and to determine the angle of twist, again we have to determine the torque, internal torque along the length of the shaft. Okay, so the applied torque is 25 into 12, that is force into lever arm. So that is the torque applied to the torque wrench. Okay, that is the applied torque. And if we consider the free body diagram of the whole assembly means the post with the torque wrench. So that will be similar to this figure number C. So here this is the applied torque, and the inserted length or buried length is 24 inches, and if we assume that the uniformly distributed torque is T, so the total torque in this length will be 24 T. So this torque will be anti-clockwise. So according to the equilibrium condition, this torque will be clockwise, and if we apply the equilibrium condition, that means the applied torque equals to internal torque. So from here we can get the value of T, that is 12.5. So it indicates that due to this applied torque, uniformly distributed torque of 12.5 pound inch per inch will be developed in this length, 24 inch length. Okay, so the maximum stress will be the torque, maximum torque times C means the remote distance by Z. Okay, by Z. So C is 1 inch because the radius of the diameter of the post is 2 inches, and from that value of diameter or radius, we can determine the sectional properties from sectional properties. So the maximum stress will be this one. Okay, now we have to determine the angle of twist. So as the torque is not concentrated along the length, one torque is concentrated, another length is very uniformly distributed. So we cannot apply this equation directly, because in this equation, the for this equation, torque will be constant or concentrated. Okay. So we have to use this equation. We have to use this equation if the internal torque depends on the length of the shaft or length of the post. Okay. So from this diagram, we have seen that the internal torque depends on the length of the shaft or length of the post. Okay. So internal torque. So we can develop a general expression for internal torque for the length BC. BC means this point is B, that point is C. So the internal torque along this length. So to do that, we can take a small segment. The length of the segment is X. So the uniformly distributed torque is 12.5 B. So the internal torque will be 12.5 times X. So that is the internal torque in the length BC or in the segment BC. Now the angle of twist, so the length above the ground surface. So here the length above this ground surface, this segment is subjected to concentrated torque. Okay, because in this length or in this segment, the concentrated torque will be similar to the applied torque. Okay, but in this segment, the torque is varying. Okay, so for segment A to B, the angle of twist will be this one. The internal torque in segment A to B, and the length of the segment, and Z. These are the Z is the metallic properties and Z is the sectional properties. And for segment BC, TBC is the internal torque, and if we consider a small segment dx, so this is the angle of twist, angle of twist for the internal torque in the segment BC, and we have the equation of general equation of TBC in the segment BC. So if we substitute that equation in this expression, so after integrating from 0 to length of BC, that means 24 inch. So so the angle of twist will be 0.00167 radian. So that is the angle of twist. And it is another problem number 9. The shaft of radius C is subjected to a distributed torque T. It is a distributed torque, not uniformly distributed. It is distributed. Okay, it is a distributed torque, not a uniformly distributed torque, because the torque is varying from support to the free end. This is the support, and A is free end, length is X. A distributed torque T, the equation of distributed torque is this one: T naught 1 plus X by L square. So T naught is the torque applied at B. Okay, so that is T naught, and X is measured from the fixed support, and L is the total length. Determine the angle of twist at end A. So what will be the angle of twist at end A, and the shear modulus is G. So first of all, we have to determine the torque developed at point B, internal torque developed at point B. So that can be determined using this equation. So that is the TB is the torque developed at the support, or the reaction at the support, and if we consider a small segment, length is dx. So the total torque in the segment dx will be T dx, and if we integrate over the length, then you will get the total applied torque. This is the applied torque, and this is the internal torque, or the support as torque at support. So substitute the equation of Tx and integrate over 0 to L. Then the torque, internal torque, or the torque developed at point B will be 4 by 3 T naught L. Okay, so that is the internal torque at point B. But we have to determine the angle of twist. So as the torque is varying over the length, so we have to use this equation T phi x, Tx dx jz, and the section is constant. Here section is constant, and z is also constant, because same material was used to make the tube. So the variable is only Tx. That means the internal torque at a location x distance from the support. So if we take an element, or if we cut the tube at a section x distance from the support, and if we draw the free body diagram, that will be similar to this one. So this is the torque developed at point B, and this is the internal torque, applied torque. So the applied torque will be this one, because from this equation we can see that the total applied torque is this one. Total applied torque is this one in length x. So that is the applied torque. This is the internal. So this one is this internal torque is clockwise, and that is anti-clockwise. So the internal torque at here will be this one minus that one. This one minus that one. This is the equation of internal torque developed at a point x distance from the support. Okay, so we can substitute this equation in this expression. So after simplifying, the angle of twist will be this one. Okay, this is nothing but the some mathematical calculation. So after calculation, the angle of twist will be 7 T naught L over L square over 12 JZ. Okay, 12 JZ, and we know if we consider C is the radius of the shaft, then J will be this one, and you can substitute here. Or again, you can keep the equation similar to this one. So J simply you will write that C is the J is the sectional polar moment of inertia of the section. Okay. Now in the previous classes we have discussed only only the circular shaft subjected to torsional force. Okay, subject to torsional force. But we considered only the circular shaft. It may be solid or it may be hollow circular shaft. But in practical field, the structure may not be always circular. Okay, may not be always circular. It may be non-circular. Okay, so for now non-circular structure, what will be the torsional formula? So look at the figure. In the for the torsional for the circular shaft, go to the slide at the very beginning. Here, look at here. What is the variation? What is the variation of the undeformed and deformed body due to the applied deformed body due to the applied torque? So in this figure, we have seen that circle remains circle. Here, circle. If we consider any one circle before deformation, after deformation, you will see that circle is still circle. Okay. Although the circle has been rotated, but the circle is still circle, and the plane section remain plane. Plane section remain plane, and the radial line on the surface remain straight line. Okay, and there is no warp wrapping or bulging. Okay, that is the observation of the structure after deformation and before deformation. But go to the non-circular shape or non-circular structure. Non-circular one. So, in case of circular shape, the circle remains circle. Okay, but look at here. If we consider any line, it means the closed line. That means it will be a rectangle. If we consider any rectangle, so before deformation, it was a rectangle. If we draw a line, a closed line on the boundary of the body, so that will be for this case, it will be a rectangle or a square. But after deformation, it was not a square or rectangle. Okay, that means the section has been deformed. Section has been deformed, but in the previous for circular shape, it was observed that section has been twisted, but it was not deformed. Okay, there is no wrapping or there is no bulging, but in this case, the surface has been in this case the surface has been wrapped. Okay, surface is not straight. So again, but the plane section remain plane. Here at the end, this section is plane. Oh no, sorry, I am wrong. The plane section is not plane because you will see there is a curvature on the section. Okay, so those assumptions will not be applicable for this non-circular shape. The cross section may bulk or wrap. And it is shown by another example. So this if we draw a rectangle or if we draw a circle on the surface of the body before applying torque, and if we apply torque on this body, then after deformation, this circle has come to this form. Okay, so this is the variation of deformation for non-circular shape compared to the circular shape. And if we show the variation of stress on the cross section, it will be similar to this one. So at this location, stress variation will be similar to this one, and at the corner, the stress variation will be this one. Okay, and the section looks like this one. Okay, it is the cross section. So wrapping of cross sectional area. So this figure indicates that the cross section has been wrapped. But at the corner, look at the corner, there no stress will be developed. Okay, at the corner, no stress will be developed. Why? Because if we say due to shear torsional force, this force will be developed. This shear force will be developed, but according to the equilibrium condition, if this shear stress is developed due to the torsional force, that this shear stress must be developed to maintain its equilibrium condition. Okay, but this end is free. This surface is free of applied stress. So, according to boundary condition, there is no applied shear stress. So as there is no stress, so there will be no stress. That means at this corner, no shear stress will be developed due to the applied torque. And this table shows some equation of maximum stress and angle of twist for some specific cross-sectional area. So look at this figure. So this figure shows that the maximum shear stress will be developed close to the angle axis of rotation. This is the axis of rotation. So maximum shear stress will be developed close to the point of axis of rotation. But it was reversed in the circular shape. In the circular shape, we saw that the maximum shear stress is developed at the remote point. That means at the at the point which is located far away from the axis of rotation. But in this case, the maximum stress will be developed close to the axis of rotation. And here, this point is the farthest distance from the axis of rotation, and there is no shear stress. There is no shear stress. So that is reverse to the circular shaft. So this table shows some equation of maximum stress and angle of twist for some specific cross-sectional area. So for a square cross-sectional area, and this one is for equilateral triangle. That means all sides are equal, and this one is for ellipse. So you can consider this equation also for circular shaft, and if you substitute the value of A and B for circular shaft, then you will see that this equation is similar to the equation for circular shaft. So you can apply these equations for ellipse, also for circular shaft. So now we can do a problem. Problem number 10. It is a shaft having a triangular cross section. One end is fixed to the support, and at the free end, a torque is applied. Okay, and the length of one side is 1.5 inch. It is an equilateral triangle. And determine the largest torque T that can be applied to the end of the shaft if the allowable shear stress is 8 ksi. Okay, allowable stress of the material that is used to make this shaft is 8 ksi. And the angle of twist at its ends, that means the angle of twist of this end will be limited to 0.02 radian. That means the angle of twist of this free end will not exceed this value. Angle of twist will be either 0.2 radian or smaller than this one, but it will not be the angle of twist will not be greater than 0.2 radian. Okay, so we have to determine the largest magnitude of largest value of applied torque that will develop the maximum shear stress below than this value, because this is the allowable shear stress, and again that will give the angle of twist at the free end similar to 0.2 radian, similar to or greater smaller than 0.2 radian. And then another problem: how much torque can be applied to a shaft of circular section made from the same amount of material? Okay, if the shaft, okay, I will explain it later. So first, for triangular section, the equation was this. The equation of maximum shear stress was this 20T AQ. So this maximum stress will be equal to the allowable stress. That's why it is tau allowable, and tau allowable is 8 into 10 to the power 3 ksi, and and A is 1.5 inch. So from this equation, we will get the maximum value of torque is 1,350 pounds. But there is another condition. Another condition is the value of maximum torque will be such that the angle of twist of this free end will be equal to or smaller than 0.2 radian. So if we consider this equation, again this equation contains the term torque. Okay, so from this equation we can get another value of maximum torque. So from this condition, from this criteria, the value of maximum torque is 170 pound inch. Okay, so to get the limiting value of shear stress, we have to apply this amount of torque. But to restrict the rotation at the free end, we have to apply 170 pound inch torque. So what will be the what will be the maximum value of torque? The maximum value of torque will be 170 pound. Okay, that will be the maximum value of torque, because if we apply this amount of torque, it will give you the maximum shear stress that will be similar to that one. But if we apply this amount of torque, the rotation at the free end will be greater than 0.2 radian. That's why the limiting value or the maximum value of applied torque will be 170 pound. Is it clear to everybody? Okay.
Yes, sir.
Okay, thank you very much. And the next question was, if the actually this shaft has triangular cross-sectional area, but if we make another shaft using same material, same amount of material, that means say to make this shaft, if it requires say 50 pound cube, say 50 pound cube material, so we can make another circular shaft having same amount of material. Okay, same amount of material. So if we maintain same length of both shafts, that is 4 feet. If we for this shaft the length is 4 feet, and for the circular shaft, if we keeps the length of the shaft is 4 feet, in that case the cross sectional area of this triangular shaft will be equals to the cross sectional area of the circular shaft, because the volume is what? Cross sectional area into length. So to maintain the same amount of material, if we keep that same length, so we have to maintain the same cross sectional area, right? So the length of the triangular area is this one, half base height. This is the base 1.5, and this is the height 1.5 sine 60 degree, because as it is equilateral triangle, so the angle between two sides will be 60 degree. Okay, so this is the angle of triangle. Okay, and this is the area. Sorry, this is the area of triangle. So to maintain the same amount of material, we have so maintain the same amount of material, we have to make the circular shaft having the cross sectional area similar to this value. So if C is the radius of the circular section, so the cross sectional area of the circular shaft will be pi c square. From here, C is this one. So that is the radius of the circular shaft. Radius of the circular shaft. Again, for to maintain to follow the stress limit criteria. To follow the stress limit criteria, so the maximum value of torque will be, so here C is this one, and tau allowable is 8,000 8 ksi, sorry 8 ksi, so it will be 8,000 psi, and as we have now the value of C radius, so we can determine the sectional properties. So from here, the maximum value of torque will be 2,170 pounds. And to maintain the angle of twisting criteria, so from here we will get another value of maximum torque. So from again, if we consider these two torque, so the maximum allowable torque will be this one, 233 pounds. So again, for circular shaft, we have seen that the applied torque depends. The limiting applied torque depends on angle of twist. That means angle of twist limits the applied torque or dominate the applied torque. Then sometimes you can see in the previous problems, we have seen circular shaft, then circular shaft may be solid or hollow, and we have discussed about the non-circular shaft. Okay, but in real field, the structure may be thin wall tube. Thin wall means thin means thin, right? That means the thickness of the material is thickness of the structure is very small. That is thin wall tube having closed cross section. Having closed cross section. So what will be the torsional formula for thin wall tube? For thin wall tube. So to derive the torsional formula, we will again consider some assumptions. Okay, or we will again consider some assumptions. So assumptions are the wall is very thin. That means we will assume the wall is very thin. But from the circular shaft, hollow circular shaft, we have seen that for circular cross-sectional area, the stress depends on the distance of the point from the axis of rotation. So from that consideration, we will see that the stress will be small at the inner surface. Shear stress will be small at the inner surface, and it will be greater at the outer surface. Okay, so along the thickness of the structure, the stress will be varying. Okay, stress will be varying. That means stress will be small at the inner surface, and it will be greater at the outer surface. So stress varies along the thickness of the section. But here, according to the assumption, the wall is very thin. So we can ignore the variation of the stress across the thickness. Okay, we can ignore that. That means the stress at the inner surface and outer surface will be almost similar. As the thickness is very small. So we can assume that the entire thickness will be subjected to uniform shear stress. Okay, or uniform shear stress will be developed across the thickness. Okay, the shear stress is uniformly distributed across the thickness. So these are the assumptions to develop the torsional formula for thin wall tubes. Now, another term is shear flow. What is shear flow? I will explain it at the later. So, if we take an element from this body, and say this one is the element, and if we draw the free body diagram of this element in a large scale, so this diagram. So this figure B shows the free body diagram of this small element, and this structure is subjected to a torque K. So shear stress will be developed here. And we can assume the thickness is not constant along the perimeter. Okay, along the perimeter, the thickness is varying. So there are two locations. One is A, another one is B. So at this location, say thickness is TA, and at here thickness is TB. And the shear stress developed at this location is tau A, and at this location tau B. Okay, and the length of the element is dx. Length means the length along the axis of rotation is dx, and the length along the perimeter of the body is S. Okay, so at this end A, the total shear stress will be shear stress times cross-sectional area. That is the shear force. Okay, shear force at section A. Total shear stress and shear force basically nothing, both are same. Okay, so the shear force developed at section A will be the shear stress at A times the area at A. So the shear stress at A is tau A, and area is thickness times length. So thickness is TA, length is dx, and the shear force developed at section B is tau B, TB dx. Okay, that means shear force acting on this surface and the shear force acting on this surface. Okay, shear force acting on the surface and shear force acting on the surface. And now, according to equilibrium condition, summation of Fx will be 0 for any kind of force. Summation of force will be 0. So this shear force is towards right, and this shear force is towards left. So if we consider this one is positive, that one will be negative. So according to equilibrium condition, this shear force will be similar to this shear force, and both are numerically equal. So this shear force is that shear force. That means this one equals to that one. Okay, this shear force equals to that shear force. So from here you can eliminate dx from both sides. So ultimately you will get these relationships: tau a ta, that means shear stress at side at end A, ta, that means thickness of the tube at A, equals to tau b, that means shear stress at end B, and tb, that means thickness at end B. Okay, and if we consider another section, again it will be tau c, tc, tau d, td. That means along the perimeter of the tube, this value will be constant, and this is known as shear flow. Okay, this is known as shear flow because it is similar to water flow. Because in case of water flow, according to Bernoulli's equation, we know at any section total flow will be constant, right? Total flow of water will be constant. If the section is narrow, velocity will be high, and if the section is larger, velocity will be smaller. That is the difference. But the total flow will be constant. For uniform flow, total flow, that means total amount of water per unit time. Say if we consider 1 hour, so in 1 hour through any section, total flow of water will be same. So that one is similar to that water flow. This stress is similar to the water flow because through this section. Because at this location, this term is that one, and at this location, stress into thickness is this one. And if we consider another section here, so all will be constant. So it is nothing. It is similar to water flow. That's why, but it is not water. It is shear stress. That's why it is known as shear flow. Okay, it is known as shear flow. And that will be clear to you when you will learn the open channel flow. I think you will have you learned it already, open channel flow?
No, sir.
Okay, so you learn it in third year, I think, in level 3. That will be in that time it will be very much clear. So this term is known as shear flow. And again, if we consider the thickness is constant, if we consider the thickness of the tube is constant, so the stress at the inner surface and stress at the outer surface will be variable. And if we determine the average shear stress through the section, then this term will be actually this one, the tau average. That means average shear stress through the section, and T is the thickness. And now, if we consider another small element along the length of the shaft, that is shown in figure C. It is another small element along the length. So along the perimeter, the length is ds. Along the perimeter, the length is ds, and along the length of the shaft, length is dx, and the thickness is t. Because this length is very small, so the thickness at this location and thickness at this location will be almost same. That's why it is t. Okay, and now so the shear stress, shear force developed on the surface. Shear force developed on the surface will be what? The shear stress multiplied by the cross-sectional area. So the shear stress is tau average. That means the average shear stress acting on these surfaces tau average, and the area of this section is T into ds. That means this length into that length, that one is ds. So the area will be T into ds, and this is the average shear stress. So the total shear stress or the shear force acting on this small element will be df, which is this. Okay, and we know tau average T equals to q, that means shear flow, and this term is constant ds. So from here q will be df by ds, and that is known as again the shear flow. So what is indicated by this equation? That is the shear force acting on the element, that is the total shear force acting on the element, and the length of the element is ds. Length of the element is ds along the perimeter. So this equation indicates that the shear force per unit length along the perimeter. Okay, so this equation indicates that the shear force per unit length along the perimeter. That is shear force, shear flow. That means force per unit length along the cross-sectional area. And what will be the equation of shear stress? And now we will derive an expression to calculate the average shear stress. Okay. Now, say again, this is the cross section of the tube. Now we can consider a small segment. We can consider a small segment. The length of the segment along the perimeter is ds, and the shear force acting on this small element is dm. Shear force acting on this small element is dm. So this force will create torsion along this axis of rotation. So the total torsion will be df into h. H is the distance from this point to the axis of rotation. So the torsional force due to this small shear force will be h, that means distance times force. And from the previous equation, we have got the expressions for df, and if we substitute here, then the small torque, that means the torsion developed due to this small torque, that will be Td, and Td is this one. Okay, so from here, this equation indicates that if we want to determine the total torque, okay, so this is the torque. This is the torque developed by the shear force, acting on this small element. Okay, so there are many small elements. So if what will be the total torque? So to determine the total torque in this equation, it indicates that the torque depends on the length of the cross section along the perimeter. Length of the perimeter. Okay, so if we to determine the total torque, we have to integrate. Along the full length. So it is nothing but a line integral. That's why it is line integral. So here tau average t, this is constant. So we can take outside the integral sign. So in the integral, it is h ds. So if we know the equation of if we can express the h in terms of s, then we can integrate. To calculate this term. But we can calculate this term by another way, that is graphical method. That is known as graphical method. In this case, we will use another term, that is mean area. Mean area means if we consider a small element here, and if we if we connect the ends of this small element to the axis of rotation, then it will form there will be a small triangle. There will be a small triangle, and as this length is very small, although it is a curved length, but as the element is very small, so we can assume it is straight. So it will be a triangle. Okay, and the area of this triangle is known as mean area. Okay, mean area. So the as it is very small, so the mean area will be designated by DAM. A is area, M for mean area, and D for a very small element. So it will be half base height. Half base is ds, height is h. Okay, height is h. So that will be the mean area. So if we want to determine the total, determine the here H's ds will be 2 times of this one, and if we substitute this equation in this expression, then the equation of torque will be this one. Equation of torque is this one. So here now the equation of torque has been expressed in terms of mean area. So if we want to the total when we have completed the integration, then A will be the total mean area. A will be the total mean area. So here this AM, that means mean area, indicates if we draw the center line of the thickness. That means center line. That means this line is located between. This line is located at the center between the inner and outer points. So this is known as center line. So this area is the area enclosed by this center line. Okay, AM is the area enclosed by this center line. So from here, the average shear stress is applied torque divided by 2 TAM. That is the average shear stress, and from this equation, the equation of shear flow will be T to AM, because shear flow is tau average into T. So this T will be eliminated. And this is the angle of twist. So how can we calculate the angle of twist using this equation? We will explain it in the next class. Okay, any question? Do you have any question? Okay, I think you do not have any question. So that's all today. Do you have any question? If you do not have any question, I will close the. I'll stop the class.